Okay, now what we want to do is, once again, we'll talk about one-dimensional plane waves, and we look at reflection, at the interface. Of two media. Okay, and this line separates the two media, and we'll have on one side a fluid with a density ρ1, speed of sound C1, and on the other side we have ρ2, C2. Remember now, ρ times C is the specific acoustic impedance that relates pressure to particle velocity. Now, let's call this the left-hand side and then the right-hand side. If sound pressure is incident on the left-hand side, and let's call this x0, what happens is some of it is reflected and some will be transmitted. Okay. Since the frequency dependence will always be the same, okay, we can drop it in writing the expressions. So what is the acoustic field on the left-hand side? Pi minus pi? Minus? Why is it minus? Plus, okay. So the on the left-hand side, total sound pressure is okay. Oops, K1. Now, what was K? That's before, yes. What was K? K was the ratio of radial frequency to speed of sound. So if the speed of sound is different on both sides, the wave number is also going to be different. Okay? In fact, that's also equal to 2 pi over lambda, lambda being the wavelength. What does this mean? What this means is when you have a particular sound wave at a frequency omega from the left-hand side, it is going to propagate to the other side at the same frequency, but the speed of sound and the wavelength are not going to be the same. Same frequency, but spatial changes do take place. So that's what you have. And of course, for the other one, you have omega over C2. So the pressure on the other side will be, could you make sure that the return has a negative in front of this? Okay. And the transmitted, or the pressure on the other side is what? It only consists of sound waves that are going away. There's nothing to reflect it back. And so one component, and how would we write that? Just some amplitude, which we do not know yet. And what is the other component? What else is there? Come on, quick, this is very simple. Very good, exponential I k2x. And always remember they have this harmonic time component, but because it doesn't change, we're just simplifying and dropping it for the time being. What are the boundary conditions? What do you think? What should that be? And how many should there be? Think physically, and it needs to make common sense. What's happening is from one fluid to the other one, pressure wave is moving through. Okay, we have particle velocity and sound pressure. As it goes through that, what can happen, what cannot happen? What happens and what doesn't happen? These are very straightforward, not complicated. Yes?
Total pressure cannot change.
Pressure needs to be the same as it goes through. What else? How many unknowns do we have? We have a number of unknowns. What about particle velocity? It needs to be continuous at the interface. If at the interface you have a pressure differential, then you have a discontinuity. You cannot have that, and you cannot have a discontinuity of particle velocity either. So they have to be continuous at the interface. So at the interface, this is important to remember, pressure and particle velocity must be continuous. These are important notions for you to follow and understand. So we understand the pressure. What is the particle velocity on the left-hand side? No different than what we have written before. So I will not redrive it. And on the right-hand side, okay, these are the particle velocities. So if we have P1 at x0 is equal to P2 at x0, and U1 at the boundary and U2 at the boundary, all we do is substitute these. Okay, if you go back to the pressure expression x0 and x0, and coming down here for this, we can say A1 plus B1 is equal to B2. And for this, we are able to write A1 minus B1. But one has to be careful here, okay, because particle velocity expressions have the impedance expressions rho C, rho 1 C1 and rho 2 C2. Okay. Well, how do we simplify this? Let's write this as let's see now. Okay. Let's see. A1, B1. Okay. Yes. And call this the ratio of the acoustic impedances, zeta number. Let's see, sorry. Okay. Combining these two using a ratio This is the reflection coefficient. Okay. No, this is A2. A1, B1, A2. Right, okay. Yes, okay. Yeah, it didn't make sense. Okay. So, this is the reflected wave and the transmitted wave. This back here. Reflection coefficient and transmission coefficient, the amplitudes of the incident, reflected, and transmitted, just as a summary. Now, one might think ordinarily that T plus R should sum up to 1, but it doesn't. We'll discuss that as soon as you finish your notes. Okay, so why would that be? Well, the amplitudes do not add up, but you need to think about it in terms of power. Okay, so in power terms, then you will see that they will add up to 1. So it's an energy conservation rather than amplitude conservation. There's no such thing. Okay, and you'll be able to demonstrate. Now, let's look at a couple of cases. If the second medium is resilient, how can we use these equations? This is little engineering approximations here, okay? Given this summary here, if the second equation is resilient, what happens? What does it mean? What's resilient mean?
Pressure is 0.
Yes, but
They are small.
exactly, right? The density and speed of sound are small. And and what does it mean in terms of these? Remember what zeta is? Let me write it here. It's the ratio of one to the other one. Okay. Now that we see this. What values do they take if the second fluid has a resilient characteristic impedance?
Coefficient will be 0, reflection coefficient will be -1.
Exactly. Okay, very simple as that. And this is something you know also. If this is resilient, meaning this is much, much less than 1, so you can approximate it to be 0. And then if it's 0, it doesn't transmit to the other side, okay? And it's almost like vacuum. And if these are 0, all the sound is reflected back. Okay, very good. Okay, now let's look at something that's a little bit different than both. What if the boundary is neither rigid nor resilient, but it's an absorbing boundary? How would we define it? Okay, so some sound will be absorbed. Not all will be reflected, not all will be transmitted, but some. Okay, that's now this is getting to be a little bit more interesting as far as modeling is concerned. Okay, let's call that sound field. In front of an absorbent reflector. Now, let me say we assume that, let's see, how do we do this? Will it confuse you if I put x in this direction? Okay. So then pressure can be written as minus Ikx. The trick in this development is how do you express the reflection coefficient? You can say it's a b, but for ease, we say it's a times some sort of a reflection coefficient, like we have used before, and it is reflecting back in the opposite direction. So the total sound pressure expression is can R be larger than 1? No. So it's got to be always, at best it can be 1 for rigid cases, or it can be 0 for pressure release. No, it cannot be 0 for pressure release. It also is -1 for pressure release. So it changes between 1 and -1. So assuming that it's, knowing that it's less than 1, what we can do is write this expression as this is 1, so let's say e to the minus Ikx is 1 plus r minus r plus r e to the Ikx. And we can combine these as okay. Okay, so the pressure expression now has two components. Let's see if we can make sense of these. Can you tell what these are? What we haven't mentioned the word standing waves. Okay, we talked about progressive waves. And so when a wave is reflected back with the equal amplitude, they build up what's called a standing wave. Okay, let me just take one moment and describe. Let's use a string. Remember, if you excite a string, okay, you have waves, and then at a rigid end, it will reflect back. And if you continue to excite it in such a way, you have these waves there, actually two progressive waves traveling in opposite direction, but when you look at it, the amplitude here is always oscillating back and forth. So this is what's called the standing waves. These are the maximum positions, antinodes, and these are the nodes. And a moment ago, when we spoke about sound pressure waves being reflected back, they form what's called a standing wave. The incident and the reflected waves form what's called a standing wave in front of a wall, as opposed to just a progressive wave. So two waves constructed together, they have a, called a standing wave. Now, when we have a partially reflecting surface, okay, the amplitude of the reflected wave is less than the incident wave. And that component, okay, that component that's equal to the incident wave's amplitude together forms a standing wave and still a progressive wave. What does this mean physically? Okay, when it continues to go in. So exactly. So what we're looking at here is this. A portion of this is reflected, okay, that's equal to part of that, and together they form a standing wave. Yet some of it continues to go in, okay, to the other side. So there's a flow of energy, which we haven't calculated, but there's a flow of energy that's always going, but at the same time there's an amplitude here. But the amplitude of that is not 2A anymore. It's less than that, okay? And in fact, the standing wave amplitude is, oops. And the standing wave amplitude is so for this standing wave, just for this component of this standing wave, as much energy travels towards the wall as it does away from the wall, just for the standing wave energy, okay? So if you look at its energy density just for a moment, energy density, if we add these, you have just substituting for pressure and corresponding particle velocity. Energy density everywhere is constant. But what we have is, okay, let me put it up here. The remaining fraction of the incident wave. Let's call that P prime. Oops. Earlier, when we had either the rigid surface or the pressure release surface, we had nodal lines. Let me just show you here. Remember, we had lambda over 4 core of a wavelength away. You had these 0 points, nodal lines. But now you no longer have nodal lines. What you do have is, okay, let me just do this. These are the absolute pressure. What now you have is these pressure minima, okay? Nodal lines or nodal points to pressure minima. Why is that? The reason we had nodal lines was incident waves and reflected waves canceled each other perfectly at that point. Now they do not cancel. They partially cancel. And there's a component that's incident, and that raises the pressure measured at that point. I want to explain something just a little bit different. When you have a microphone in your hand, and let's say we are radiating sound in an open field, okay? There are no boundaries, so there's no sound that's reflected. And you have a microphone you're measuring, and the pressure in time will, of course, have this either some harmonic expression. That's all it is. Now, and that has a maximum value, pressure max, okay, and it oscillates in time. Okay? If you move the microphone a little bit further, a little bit closer, etc., or this way, that way, it changes very little. Or especially if you're really far away, if it is plane wave, it shouldn't change. Now, however, the same waves, now I do put a wall here. Okay, pressure goes, and now is reflected back, perfectly reflected backwards. Okay, now I take the same microphone, I measure them. Okay, at some point, it is going to give the same type of response, but as I move, that amplitude may shrink to eventually 0 or some minimum value, and as I move it, it goes up. The reason for that is what I just tried to describe earlier. Okay, the reflected waves add up or interfere with the incident waves. So this, what we would call is standing waves are formed. So depending on where your microphone is in this, you have either a very high value or a very low value. That's the difference. And you can actually see this with a microphone, just moving it around in such circumstances. If you can visualize these in your mind's eye, it will make it easier to understand what we have derived a moment ago. Any questions on these? What we have covered essentially are plane waves, normal incidence, being reflected back by either a rigid wall, pressure release wall, or a characteristic in between. And then we also looked at the same normal incidence when there are two fluids, what happens when it moves to the other side. Now, the next topic we'll do is what happens if they are not normal, but they're moving at an oblique incidence. So there is the wall or the boundary. Now when they reflect, they're not coming back in the same direction, but they're going off in a different direction. This changes things a little bit. And this will become important later on when sound transmission takes place through walls, structures, and so on. Okay? Let's continue on that. Okay, so let's call this plane waves. But instead of normal, we call this oblique incidence. And we'll again start with a rigid surface. Now we need another coordinate, this still being x. You have a plane wave, wave fronts parallel to each other, but in a particular direction. Angle of incidence, and then they're reflected again as plane waves with an amplitude PR and angle of reflection theta r. What we do now is do exactly what we have done before, writing down the expressions for incident and reflected waves, and and summarize and sum them up using the boundary conditions, find out what the relative angles and amplitudes are. So one thing we do is, first of all, the incident wave and amplitude, capital P I, and let's call these Ik and NXX and ZZ minus I omega T. And reflection Okay. And here we're trying to simplify it a little bit, but cosine theta I, and this is nx prime. Nx prime is cosine theta of reflection, and z is sine theta I, and z prime is sine theta reflection. Okay. These are the expressions that you would use for two-dimensional sound pressure waves in under any circumstances. But let's look at the rigid surface. Case of rigid surface. Okay, meaning an impenetrable surface. Again, what is the boundary condition for rigid surface? Particle velocity must be 0. But particle velocity in what direction? See, the waves are traveling, as you can see, at an incident angle, reflected angle. But we're talking about a boundary condition, which says, because it's a rigid surface, boundary condition must be 0. Well, sorry, the particle velocity must be 0. But particle velocity is a vectorial quantity, so it must have a direction. Which direction are we referring to? What does your knowledge tell you about the direction? Say again? X-axis, yes, exactly. So it has to be normal to the surface. That's all we know. Okay, normal to the surface. So particle velocity u of x at x equal to 0 must be 0. Okay, this component. And so that's an important element for you to consider. Not in that direction, because we have no knowledge what the component of particle velocity is in tangential direction. We don't know that. But what we do know is it cannot move normal to the surface. Okay? Important element, and you will face this later on. And just to remind you one more time, the relationship between acceleration of particle times the density was the gradient with respect to some direction. So with those in mind, you can say u of x at x0 can be expressed as okay. Let's see what we can get out of these. You can see the components when you take a derivative with respect to x, I, k, and nx. The angle is now going to get involved, okay? And so we have nx. Take a look at this equation. This is a very interesting equation. Now, what is the requirement? Can you read this? Oops, yeah. What is the requirement here for this equation to be satisfied? Okay. You have nx, which is an angle, cosine. Okay. You have the reflected angles, cosine. 2 amplitudes, and 2 exponential functions. For this equation to hold, to be equal to 0, definitely the arguments of the exponents must be the same. Okay? That's a condition. Doesn't matter what these are. They must be equal as functions. So the first thing we say is arguments of exponents. Must be the same. Otherwise, it will not become equal to 0. And what that means then is, oops, nz is equal to nz prime, and that tells us that sine theta I is equal to sine theta r very simply, incident and reflected angles must be equal. And if that's the case, you have that. And if that's the case, we can write the sound pressure as incident and from the rigid boundary condition, we also know that incident and pressure are incident and reflected pressure amplitudes are the same. So finally, we would have this is, I want to describe something here before I let you go. Okay. Okay. Now, when you look at the incident wave, okay, you can think about it in terms of a component of it propagating in the z direction and a component propagating towards the boundary. Okay, take a look at the reflected wave. The reflected wave has a component that's propagating along the z direction and a component that's propagating away from the boundary. Okay, so the part that goes towards and comes back together form a standing wave, just like a plane wave that's normal incidence going and coming back. Whereas the ones that are moving along z, both the incident and the reflected, have only a propagating wave. There's no reflection in the z direction. And how did we obtain all of this? By simply writing the equations as if we do not know what the amplitudes are, which we don't, or the relationship between them, but we did write, just in general terms, incident and reflected pressure angles, but we did know the boundary condition. The key here that you need to remember is the boundary condition was particles velocity is 0, but only normal. Okay, that's how you would measure it anyway. When you put an accelerometer, you don't measure the particle velocity in the other direction, tangential direction. It's normal, always. And using that, we're able to establish that for a rigid surface, the incident and reflected wave angles are the same, and reflections in the x direction form a standing wave. Okay? Next time, we will continue on the oblique waves and then move into waveguides. What I mean by waveguide is what happens as sound propagates in a duct, and if you have loudspeakers, etc., how it moves up, sound cancellations, and so on. Thank you. Any questions? No? Okay, thanks very much.